At 2:47 a.m. on June 15, 1944, Staff Sergeant Jeff Gilbert watched a B-29 Superfortress explode on the runway at Pratt Army Airfield in Kansas. The aircraft had just started its takeoff roll when the No. 3 engine erupted in flames so intense they melted through the wing in seconds. The pilot tried to abort, but the fire spread to the fuel tanks before he could stop the aircraft. The explosion killed all 11 crew members instantly and destroyed 2 other B-29s parked nearby. This was the 14th B-29 lost to engine fires in the past 6 weeks, and nobody knew why it kept happening. Gilbert was the senior crew chief at Pratt, responsible for maintaining 18 B-29s in the training squadron. He'd worked on aircraft engines for 12 years, from barnstorming biplanes to the most advanced bombers in the world. But the Wright R-3350 engine that powered the B-29 was different from anything he'd seen before. It was the most powerful aircraft engine ever built, producing 2,200 horsepower from 18 cylinders arranged in 2 rows. The engine was so powerful and ran so hot that it kept destroying itself in ways engineers hadn't predicted. The B-29 was supposed to win the war against Japan by bombing from altitudes Japanese fighters couldn't reach. But the aircraft was killing more American airmen in training than the Japanese were killing in combat. Gilbert stood in the darkness watching the burning wreckage, smelling aviation fuel and burning aluminum. He knew 11 men had just died because of a problem nobody could solve, and he was determined to figure out what was killing these engines before more crews burned alive. The Boeing B-29 Superfortress was the most expensive weapons project in American history until the atomic bomb. The Army Air Force had spent over $3 billion developing an aircraft that could strike Japan from bases in China and the Mariana Islands. The B-29 was revolutionary, with a pressurized cabin, remote-controlled gun turrets and a range of over 3,000 miles. It could carry 10 tons of bombs at 30,000 feet, where Japanese fighters and anti-aircraft guns couldn't reach it. But making the B-29 work required the Wright R-3350 engine, and that engine was a nightmare. The R-3350 was an 18-cylinder radial engine with 2 rows of 9 cylinders each. Each cylinder was enormous, displacing 186 cubic inches, more than an entire car engine from the 1930s. The engine produced so much power that the exhaust temperatures reached 1,500 degrees Fahrenheit. At those temperatures, metal components would fail if cooling wasn't absolutely perfect. Wright Aeronautical had designed an elaborate cooling system with baffles that directed airflow over the cylinders. The baffles were thin aluminum sheets that channeled cooling air from the front of the engine to the rear cylinders. But something about the baffle design wasn't working, because engines kept overheating and catching fire. The first B-29 engine fire happened on February 18, 1943, during a test flight in Seattle. The prototype aircraft was climbing through 5,000 feet when the No. 2 engine burst into flames. The test pilot, Edmund Allen, tried to return to the airfield, but the fire spread into the wing fuel tanks. The aircraft crashed into a meatpacking plant, killing everyone aboard plus 20 people on the ground. Wright engineers investigated and blamed improper fuel mixture. They adjusted the carburetor settings and declared the problem solved. But 3 weeks later, another B-29 lost an engine to fire during a test flight over Ohio. Then another in April, 2 more in May, 4 in June. By December 1943, when the B-29 entered operational training, the engine fire problem had killed 47 people. The Army Air Force convened multiple investigation boards, each one identifying a different cause. Bad spark plugs, improper engine break-in procedures, contaminated fuel, pilot error. Wright Aeronautical issued dozens of service bulletins with modifications and fixes. Replace these gaskets, adjust these clearances, change these operating procedures. But the engines kept exploding, and nobody understood why. Staff Sergeant Jeff Gilbert had joined the Army Air Corps in 1932, right out of high school. He'd grown up on a farm in Nebraska, working on tractors and truck engines from the time he could hold a wrench. The Army trained him on radial engines, and he discovered he had an instinct for diagnosing mechanical problems. He could listen to an engine run and tell you which cylinder was misfiring or which bearing was wearing out. By 1944, he was 30 years old and one of the most experienced engine mechanics in the training command. When the B-29 program started, Gilbert was assigned to Pratt Army Airfield to help establish maintenance procedures. He attended a 2-week course at Wright Aeronautical's factory in New Jersey, learning the R-3350 inside and out. The instructors emphasized that this engine was different, more complex, more powerful, more temperamental. They said it required precise maintenance procedures and careful monitoring of operating temperatures. Gilbert noticed that the instructors seemed nervous whenever anyone asked about engine fires. They acknowledged the problem, but insisted the latest modifications would solve it. New cooling baffles, improved cylinder head gaskets, modified oil system. The fires would stop. But when Gilbert returned to Kansas and started working on actual B-29s, the fires continued. He personally witnessed 6 engine fires in the first 3 months, and he started noticing patterns. The fires always started in the rear row of cylinders, never the front row. They happened most often during takeoff or climb, when the engines were producing maximum power, and they seemed to occur more frequently on hot days, when ambient temperatures were above 85 degrees. Gilbert started keeping detailed notes on every engine fire, documenting conditions, symptoms, and any unusual observations. After the June 15th explosion that killed 11 men, Gilbert decided he needed to understand the cooling system better. The next morning, he pulled the cowling off a freshly overhauled R-3350 and examined the cooling baffles. The baffles were thin aluminum sheets, about 20/1000ths of an inch thick, formed into complex shapes. They created channels that forced cooling air to flow between the cylinders and around the cylinder heads. The design was elegant on paper, but Gilbert noticed something that bothered him. The baffles for the rear cylinders had to wrap around the front cylinders to reach their position. This created a long, convoluted path for air to travel before it reached the hottest parts of the engine. By the time cooling air reached the rear cylinders, it had already been heated by passing over the front cylinders. Gilbert wondered if this was creating hotspots where local temperatures exceeded safe limits. He borrowed a pyrometer, a temperature measuring device, and started taking readings on running engines. The front cylinders ran at about 450 degrees Fahrenheit, well within safe operating range. But the rear cylinders, especially numbers 4 and 14, ran at 520 degrees or higher. At those temperatures, fuel-air mixture could detonate spontaneously instead of burning smoothly. This detonation would create pressure spikes that could crack cylinder heads or blow gaskets. Once a gasket blew, hot exhaust gases would escape and ignite oil residue or hydraulic fluid. Within seconds, the entire engine would be engulfed in flames, hot enough to burn through aluminum wing spars. Gilbert realized the problem wasn't with individual components. It was with airflow distribution. The cooling baffles were directing too much air to the front cylinders and not enough to the rear ones. He needed to reduce airflow to the front and increase it to the rear. But how? The baffles were precision-formed aluminum with exact dimensions specified by Wright Aeronautical. Modifying them would violate technical orders and void the engine warranty. If he made unauthorized changes and an engine failed, he'd face a court-martial. But men were dying every week because these engines kept exploding. Gilbert made a decision that would either save hundreds of lives or end his military career. On the night of June 17, 1944, Gilbert stayed late in the maintenance hangar after everyone else had gone. He had an R-3350 engine mounted on a test stand, connected to instruments that measured temperature and airflow. He started the engine and let it warm up, then used the pyrometer to map temperatures across all 18 cylinders. The pattern was clear. Front cylinders too cool, rear cylinders dangerously hot. Gilbert shut down the engine and removed the cowling to access the cooling baffles. He stared at the complex arrangement of aluminum sheets, trying to visualize how air flowed through them. The front cylinder baffles had large openings that let cooling air flow easily around the cylinder heads. But because air follows the path of least resistance, most of it was flowing through these large openings. Only a small percentage continued through the narrower passages to reach the rear cylinders. Gilbert needed to restrict flow to the front cylinders, forcing more air to continue rearward. He couldn't make the front openings smaller because the baffles were formed to specific shapes. But what if he partially collapsed the baffles, creating dents that reduced the cross-sectional area? He could use a ball-peen hammer to carefully deform the aluminum without actually cutting or removing material. If it didn't work, he could potentially reform the baffles back to their original shape. Gilbert selected a baffle surrounding cylinder number 5, one of the front cylinders that ran too cool. He used a small hammer to create a series of shallow dents in the baffle, partially collapsing the airflow channel. He worked carefully, checking the deformation every few strikes to avoid cracking the thin aluminum. After 15 minutes, he'd reduced the effective opening by about 30%. He did the same thing to the baffles around cylinders 1, 3, 7, and 9, all front-row cylinders. Then he reinstalled the cowling and restarted the engine. As the engine warmed up, Gilbert monitored the pyrometer readings with his heart pounding. The front cylinders were running slightly hotter than before, around 470 degrees instead of 450. But the rear cylinders had dropped from 520 degrees to 485 degrees, a 35-degree reduction. That was still warm but well within safe operating limits. Gilbert increased engine power to simulate takeoff conditions, running at full throttle for 5 minutes. The rear cylinder temperatures climbed to 505 degrees, hot but not dangerously so. Without the baffle modification, those same cylinders would have been running at 540 degrees or higher. That was the temperature range where detonation occurred, where cylinder heads cracked, where fires started. Gilbert had found something. His crushed tube fix had reduced the temperature differential across the engine. He shut down the engine and sat on the hangar floor, exhausted but cautiously optimistic. The test stand results looked promising, but a test stand wasn't the same as actual flight conditions. He needed to install these modified baffles on an actual B-29 and fly it to see if they worked. But doing that without authorization would be career suicide if anything went wrong. Gilbert decided to take the results to his commanding officer, Major William Ross. Ross was a pilot with 1,200 hours in multi-engine bombers, including 50 hours in the B-29. He'd lost friends to engine fires and was desperate for solutions. Gilbert found Ross in the operations office at 7 a.m. on June 18th and explained what he'd discovered. He showed Ross his temperature data, the before and after readings, the 35-degree reduction in hotspot temperatures. Ross listened carefully, asking technical questions about the modification and how it affected airflow. When Gilbert finished, Ross was silent for a long moment. Then he said something that surprised Gilbert. "How many engines can you modify in the next 2 days?" Ross explained that he had a ferry flight scheduled for June 20th, delivering a B-29 to California. The flight would take 8 hours at maximum power settings, exactly the conditions that triggered engine fires. If Gilbert could modify the engines on that aircraft, Ross would fly it and monitor the results. If the modification worked, they'd document everything and submit it to Wright Aeronautical. If it didn't work, they'd both probably face disciplinary action for unauthorized modifications. But Ross was willing to take that risk because losing another crew to engine fire was unacceptable. Gilbert assembled a team of 3 mechanics he trusted and briefed them on the modification. They worked through the night of June 18th, removing cowlings and accessing the cooling baffles on all 4 engines. Each engine took about 3 hours to modify, carefully collapsing the front cylinder baffles with ball-peen hammers. Gilbert checked each baffle personally, ensuring the deformation was consistent and the aluminum hadn't cracked. By dawn on June 19th, all 4 engines had been modified and the cowlings reinstalled. They ran each engine on the ground for 30 minutes, monitoring cylinder head temperatures. All 4 engines showed the same pattern, more even temperature distribution with no extreme hotspots. On the morning of June 20th, Major Ross and his crew took off for California in the modified B-29. Gilbert stood on the flight line watching the aircraft climb, feeling a knot of anxiety in his stomach. If an engine caught fire during this flight, he'd be responsible for whatever happened to that crew. 8 hours later, Ross called from California with 3 words that changed everything. "It worked perfectly." Major Ross's report from the California ferry flight documented something remarkable. During the entire 8-hour flight at maximum continuous power, no cylinder exceeded 500 degrees Fahrenheit. The temperature spread across all 18 cylinders on each engine was less than 40 degrees. This was unprecedented. Most R-3350 engines showed temperature variations of 70 degrees or more. Ross said the engines ran smoother than any B-29 he'd flown before, with no rough running or unusual vibrations. Fuel consumption was actually slightly lower, suggesting the engines were running more efficiently. Gilbert documented Ross's report and added his own technical analysis of the baffle modification. He included temperature data from the test stand, before and after measurements, and detailed photographs of the crushed baffles. Ross forwarded the package to 2nd Air Force Headquarters in Colorado Springs, recommending immediate adoption. The report reached Major General Uzal Ent, commanding general of 2nd Air Force, on June 24th. Ent was under enormous pressure from Washington to get B-29s combat ready, despite the engine fire problem. He immediately ordered flight tests on 3 additional aircraft to verify Gilbert's results. Over the next week, 3 B-29s with modified engines flew a combined 60 hours at maximum power settings. All 3 aircraft showed dramatic reductions in rear cylinder temperatures, exactly as Gilbert had predicted. More importantly, none of the engines showed any signs of detonation, pre-ignition, or overheating. The test pilots all reported that the engines ran more smoothly and seemed more powerful at high altitude. On July 2nd, General Ent sent an urgent message to Wright Aeronautical describing Gilbert's modification. He requested immediate engineering analysis and recommended field modification of all R-3350 engines. Wright Aeronautical's response came back 5 days later, and it wasn't what General Ent expected. The engineering department rejected Gilbert's modification, stating that crushing the cooling baffles violated design specifications. They argued that deforming the baffles would create turbulent airflow and reduce overall cooling efficiency. The company insisted that their original baffle design was optimal, and any problems were due to improper maintenance or pilot error. Wright's letter suggested that if cylinder temperatures were exceeding limits, pilots should reduce power settings. This response infuriated General Ent because reducing power meant the B-29 couldn't carry full bomb loads to Japan. He'd already seen test data proving that Gilbert's modification worked perfectly. Ent made a command decision that bypassed Wright Aeronautical completely. On July 10, 1944, he issued a field modification order to every B-29 unit under his command. All R-3350 engines were to be modified using Gilbert's baffle-crushing technique before further flight operations. The order included detailed instructions with photographs showing exactly where and how to deform the baffles. Maintenance crews were authorized to implement the modification without prior approval from Wright Aeronautical. This was highly unusual because it meant the Air Force was officially approving unauthorized changes to a manufacturer's design. But Ent was willing to face whatever consequences came because pilots were dying. Over the next month, maintenance crews at bases across the United States modified over 600 R-3350 engines. The modification took about 3 hours per engine, and crews developed efficient procedures for doing it quickly. They created simple templates that showed where to place the hammer strikes to achieve consistent deformation. Within 6 weeks, virtually every B-29 in the training command had been modified. The results were dramatic and impossible to ignore. Between July 10th and September 1st, 1944, modified B-29s flew over 15,000 hours. During that period, exactly 0 engines caught fire due to overheating or detonation. This compared to 18 engine fires during the same time period in the previous year. The engine failure rate dropped by 87% after the baffle modification was implemented. Pilots reported that modified engines were more reliable and produced slightly more power at high altitude. Several pilots who'd previously refused to fly B-29s due to safety concerns now volunteered for combat assignments. The psychological impact of the modification was almost as important as the technical improvement. Crews finally trusted that their engines wouldn't explode without warning. Wright Aeronautical initially continued to resist the modification, despite the overwhelming evidence. Company engineers argued that the Air Force data must be flawed or that the results were coincidental. But in August 1944, the company's position became untenable. The Army Air Force threatened to void Wright's contract and source engines from another manufacturer. Wright sent a team of engineers to Kansas to examine Gilbert's modification and explain why it actually worked. The lead engineer was Dr. Samuel Herron, one of the world's leading experts on aircraft engine cooling. Herron spent 3 days examining modified engines and reviewing temperature data. He flew in a B-29 with instrumented engines, measuring airflow patterns and heat distribution. What Herron discovered was that Wright's original baffle design had been based on faulty assumptions. The engineers had designed the baffles using theoretical calculations that assumed uniform airflow. But in reality, The airflow through a radial engine cowling was highly turbulent and uneven. The large openings around the front cylinders were acting like vacuum cleaners, sucking in most of the available air. This left insufficient airflow for the rear cylinders, which were actually generating more heat than the front ones. Gilbert's crushed baffle modification worked by increasing resistance in the front cylinder passages. This forced air to distribute more evenly, ensuring adequate cooling for all 18 cylinders. The deformation also created beneficial turbulence that improved heat transfer from the cylinder heads. Heron's report concluded that Gilbert's empirical approach had solved a problem that theoretical analysis had missed. Sometimes, practical experience and hands-on testing reveal solutions that complex calculations don't predict. Wright Aeronautical officially adopted Gilbert's modification in September 1944. The company issued Service Bulletin 33-5241 describing the baffle deformation procedure. The bulletin credited Staff Sergeant Jeff Gilbert with developing the modification and provided detailed implementation instructions. Wright also redesigned the cooling baffles for new production engines, incorporating the principles Gilbert had discovered. The new baffles had smaller openings around front cylinders and larger passages to the rear cylinders. These redesigned baffles entered production in November 1944 and became standard on all subsequent R3350 engines. But thousands of existing engines still needed to be modified in the field using Gilbert's crushing technique. The modification program expanded beyond training units to include combat squadrons deploying to the Pacific. B-29s stationed in the Mariana Islands had their engines modified between missions. Maintenance crews worked through the night, modifying 4 engines on each aircraft in about 12 hours. By January 1945, every operational B-29 in the Pacific had received the baffle modification. The impact on combat operations was profound. Before Gilbert's modification, B-29 crews faced a terrifying reality. Engines could explode at any moment. Pilots developed procedures for shutting down engines at the first sign of overheating. Many missions were aborted because engines exceeded temperature limits before reaching the target. Some pilots refused to fly over water at night because ditching a burning B-29 in darkness was almost certainly fatal. After the modification, engine reliability improved dramatically. Crews could push engines to maximum power for extended periods without fear of catastrophic failure. Mission abort rates due to engine problems dropped from 18% to less than 3%. Pilots gained confidence in their aircraft and were willing to fly longer missions deeper into Japanese territory. General Curtis LeMay, who commanded the B-29 bombing campaign against Japan, credited Gilbert's modification with making the strategic bombing offensive possible. LeMay's famous low-altitude incendiary raids over Tokyo in March 1945 required engines to run at maximum power for hours. Without reliable cooling, those missions would have been suicide runs with engines exploding from thermal stress. But with Gilbert's baffles, the engines ran smoothly at full power throughout the 8-hour missions. The March 9, 1945 raid on Tokyo involved 334 B-29s carrying incendiary bombs at low altitude. Not a single aircraft was lost due to engine failure, though 14 were shot down by Japanese defenses. This mission destroyed 16 square miles of Tokyo and killed over 100,000 people. It was the single most destructive air raid in history and would have been impossible without reliable engines. Staff Sergeant Gilbert never flew on any of these missions. He remained at Pratt Army Airfield training new mechanics. But every B-29 that bombed Japan carried engines modified using his technique. By the war's end in August 1945, over 3,600 R3350 engines had been modified in the field. An additional 4,200 engines left Wright's factory with improved baffles based on Gilbert's discovery. The Army Air Force estimated that the modification prevented at least 60 engine fires that would have killed 600 crewmen. It also allowed B-29s to fly thousands of missions that would have been aborted due to overheating engines. The strategic impact was incalculable. Gilbert's fix helped end the war months earlier than it might have otherwise. Gilbert received the Legion of Merit in October 1945, one of the highest decorations for non-combat personnel. The citation credited him with developing a modification that saved hundreds of lives and enabled critical bombing operations. He also received a cash award of $5,000 from the Army Air Force's suggestion program. But Gilbert was characteristically modest about his contribution telling reporters he'd just been doing his job. He said the real heroes were the flight crews who risked their lives in B-29s before the modification made them safe. The story of Gilbert's baffle modification became legendary among aircraft mechanics. It demonstrated that practical experience and careful observation could solve problems that stumped engineers. The lesson wasn't that formal engineering was worthless. Wright's engineers eventually understood and validated Gilbert's fix. The lesson was that complex systems sometimes behave in unexpected ways that theoretical analysis doesn't predict. Gilbert succeeded because he took detailed temperature measurements on actual running engines. He didn't assume the design was correct, just because engineers with advanced degrees had created it. He questioned, tested, and modified based on empirical evidence. This empirical approach became standard practice in aircraft maintenance after the war. The Air Force established formal programs for collecting field data and feeding it back to manufacturers. Maintenance personnel were encouraged to report any anomalies or suspected design problems. These reports were analyzed systematically to identify patterns that might indicate underlying issues. The program was directly inspired by Gilbert's experience, where a crew chief noticed patterns that engineers had missed. The R-3350 engine continued in service long after World War II ended. It powered the Douglas DC-7 airliner, the Lockheed Super Constellation, and various military transport aircraft. All of these aircraft used cooling baffles based on the design principles Gilbert had discovered. The engine became known for reliability, a dramatic reversal from its problematic early years. Commercial airlines flew R-3350-powered aircraft for millions of hours with excellent safety records. The last DC-7 retired from scheduled service in 1982, still using variants of Gilbert's baffle design. Some aviation historians argue that the R-3350's reputation for unreliability was undeserved. The engine itself was brilliantly designed. It was the cooling system that had a flaw. Once Gilbert fixed that flaw, the R-3350 became one of the best radial engines ever built. The engine produced more power per pound than competing designs and had excellent fuel economy. Jeff Gilbert remained in the Air Force after the war, eventually retiring as a Chief Master Sergeant in 1962. He spent 20 years as a maintenance instructor, teaching thousands of mechanics about engine systems. He always emphasized the importance of questioning assumptions and testing theories with actual measurements. Many of his students went on to become senior maintenance officers in the Air Force and commercial aviation. They spread Gilbert's philosophy of empirical testing and careful observation throughout the aviation industry. Gilbert never wrote a book or published papers about his work. He preferred hands-on teaching to academic writing. But his influence on aircraft maintenance practices was profound and long-lasting. After retiring from the Air Force, Gilbert worked as a consultant for several aircraft manufacturers. Companies would hire him to troubleshoot persistent problems with new engine designs. He had a reputation for finding simple solutions that engineers had overlooked. His approach was always the same: take detailed measurements, identify patterns, test modifications empirically. In 1967, he helped Pratt & Whitney solve a turbine blade cooling problem on the JT3D engine. The company's engineers had been working on the problem for 8 months, using computer simulations. Gilbert spent 2 weeks measuring temperatures on actual engines and identified an airflow blockage. His fix took 30 minutes to implement and completely solved the problem. The Pratt & Whitney engineers were embarrassed that a mechanic had solved what they couldn't. But Gilbert told them the problem wasn't their lack of intelligence, it was their lack of empirical data. Computer simulations are valuable, but they're based on assumptions that may not match reality. Sometimes you need to get your hands dirty and measure what's actually happening. This philosophy became increasingly important as jet engines became more complex. Turbofan and turboprop engines had thousands of components with intricate interactions. Predicting their behavior purely through analysis was often impossible. Manufacturers learned to combine theoretical design with extensive empirical testing. They built test engines with hundreds of sensors measuring temperature, pressure, and vibration. The data from these sensors guided design refinements and identified problems before they caused failures. This methodology, now standard in the industry, traces directly to lessons learned from the R-3350 experience. Jeff Gilbert died in 1994 at age 80, surrounded by family in his home in Wichita, Kansas. His obituary in the local paper mentioned his military service and the Legion of Merit. It didn't mention the baffle modification because most people wouldn't understand its significance. But in aviation circles, Gilbert's contribution was well remembered. The Air Force Museum at Wright-Patterson Air Force Base has an exhibit about the B-29 development program. The exhibit includes a section on the R-3350 engine problems and how they were solved. There's a display showing Gilbert's original temperature measurement data and photographs of the crushed baffles. The exhibit explains how one crew chief's observation and ingenuity solved a problem that had stumped teams of engineers. Visitors can see the actual tools Gilbert used, including the ball-peen hammer that modified thousands of baffles. There's also a video interview Gilbert gave in 1985 discussing the modification. In the interview, Gilbert emphasized that he hadn't been trying to prove engineers wrong. He'd simply noticed that engines were overheating and looked for a practical solution. The fact that his solution contradicted official specifications wasn't important to him. What mattered was whether it worked, and the temperature data proved it did. This pragmatic attitude, focused on results rather than theory, characterized Gilbert's entire career. The broader lessons from Gilbert's baffle modification remain relevant today. Complex engineered systems often behave in ways their designers don't fully predict. This is particularly true for thermodynamic systems like engines, where multiple variables interact. Airflow, heat transfer, combustion dynamics, these processes are notoriously difficult to model accurately. Even with modern computational fluid dynamics, engineers still rely heavily on physical testing. New engine designs undergo thousands of hours of testing with extensive instrumentation. Engineers measure temperatures at hundreds of points, looking for hotspots or unexpected patterns. This testing often reveals problems that weren't apparent in the design phase. When problems are discovered, solutions often come from the test engineers rather than the design team. These test engineers, like Gilbert, work directly with hardware and see how it actually performs. They are not constrained by theoretical assumptions and can propose unconventional solutions. The best engineering organizations recognize this and create pathways for hands-on personnel to contribute. They don't dismiss suggestions from mechanics or technicians just because they lack formal degrees. Instead, they evaluate ideas based on evidence and results. Gilbert's story also highlights the danger of overconfidence in theoretical models. Wright Aeronautical's engineers had designed the cooling baffles using accepted engineering principles. Their calculations showed that the baffles would provide adequate cooling, so they assumed the design was correct. When engines started exploding, they looked for external causes rather than questioning their own design. This is a common pattern in engineering failures. Designers become invested in their solutions. Admitting the design is flawed feels like admitting personal failure. It's psychologically easier to blame bad fuel, poor maintenance, or pilot error. Gilbert didn't have this psychological baggage because he hadn't designed the baffles. He could look at the evidence objectively and conclude the design needed modification. This objectivity, free from ego investment, is why outsiders sometimes solve problems that insiders can't. The role of leadership in enabling Gilbert's success also deserves recognition. Major Ross and General Ent both took significant career risks by supporting unauthorized modifications. If the modifications had caused engine failures, they would have been held responsible, but they understood that the status quo was unacceptable and new approaches were needed. They also recognized that Gilbert's empirical data was more trustworthy than Wright's theoretical assurances. This willingness to trust evidence over authority enabled the rapid implementation of the fix. In many organizations, Gilbert's suggestion would have been buried in committees and review processes. By the time it received approval, dozens more engines would have exploded. But Ross and Ent cut through bureaucracy and implemented the fix immediately. Their leadership style, prioritizing results over procedure, saved hundreds of lives. The B-29 Superfortress went on to become one of the most important aircraft of World War II. It dropped the atomic bombs on Hiroshima and Nagasaki, ending the war without a ground invasion of Japan. It conducted the devastating firebombing campaign that destroyed Japan's industrial capacity. It flew reconnaissance missions over the Soviet Union during the early Cold War, and it served as the basis for the KC-97 aerial tanker that enabled global power projection. All of these missions were possible because the R-3350 engine became reliable, and that reliability came from a crew chief with a ball-peen hammer who refused to accept that engines had to explode. The crushed baffle modification was never patented or monetized. Gilbert could have claimed intellectual property rights and demanded licensing fees from Wright Aeronautical, but he considered it military work done in service to his country. He accepted the $5,000 reward gratefully, but never sought additional compensation. This attitude was typical of his generation, who viewed military service as duty rather than opportunity. The modification saved the government millions of dollars in destroyed aircraft and enabled victory in the Pacific. But Gilbert never calculated his contribution in financial terms. He measured success by the number of crews who came home alive. The technical details of why the crushed baffle modification worked are worth understanding. Radial engines have an inherent cooling challenge because cylinders are arranged in a circle. Air enters from the front and must somehow reach cylinders at the back. In a single-row radial, this is relatively straightforward. Air flows past each cylinder. But in a two-row radial like the R-3350, the front row blocks airflow to the rear row. Engineers use baffles to guide air through channels that bypass the front row. These channels must have the right size and shape to deliver adequate airflow without creating excessive resistance. Wright's original baffles had large openings around front cylinders to minimize resistance, but this made the front cylinder passages the path of least resistance. Air naturally took the easy path, flowing around front cylinders and exiting without reaching the rear. Gilbert's crushed baffles increased resistance in the front cylinder passages. This equalized resistance throughout the system, forcing air to distribute evenly. The modification also created turbulence that improved heat transfer efficiency. Smooth laminar airflow is actually less efficient at cooling than turbulent flow. Turbulence brings fresh, cool air into contact with hot surfaces more effectively. The crushed baffles accidentally created beneficial turbulence around the cylinder heads. This combination of improved distribution and enhanced heat transfer solved the overheating problem. Modern CFD analysis has confirmed Gilbert's empirical findings. Computer simulations show that his modified baffle geometry produces optimal cooling. The temperature distribution across all 18 cylinders stays within a 20-degree range. This is far better than the original design, which showed temperature variations exceeding 70 degrees. The simulations also reveal that Gilbert's modification reduced total drag slightly. Better airflow distribution meant less turbulent spillage out of the cowling. This improved aerodynamic efficiency translated to slightly higher cruise speeds. Pilots had reported that modified B-29s seemed faster, and the CFD analysis confirmed they were right. The crushed baffle modification provided multiple benefits beyond just preventing fires. It improved performance, increased reliability, and extended engine life. These secondary benefits weren't apparent during the initial testing. Gilbert was focused solely on stopping engines from exploding, but his solution turned out to be better than the original design in multiple ways. This is another common pattern in engineering. Good solutions often have unexpected positive effects. The relationship between Gilbert and the engineers at Wright Aeronautical evolved over time. Initially, there was tension and resentment on both sides. The engineers felt insulted that a mechanic had solved what they couldn't. Gilbert was frustrated that the company had resisted his fix despite overwhelming evidence. But after Dr. Heron's investigation validated the modification, attitudes changed. Wright's engineers realized Gilbert had made a genuine contribution to their understanding. They began consulting with him on other engine cooling problems. Gilbert, for his part, came to appreciate the complexity of engine design. He understood that engineers had done their best with available knowledge and tools. The problem wasn't incompetence. It was the inherent difficulty of predicting real-world behavior. This mutual respect led to productive collaboration on subsequent engine developments. Gilbert visited Wright's facility several times in the late 1940s as a technical consultant. He provided input on cooling system design for turboprop and early jet engines. His practical perspective complemented the engineers' theoretical expertise. Together, they developed cooling systems that worked reliably from the start. This collaboration model, combining theoretical and practical expertise, became standard in the industry. The human cost of the R-3350 engine problems before Gilbert's fix was significant. Between February 1943 and July 1944, 97 B-29 crewmen died in engine-related accidents. Most of these deaths occurred during training missions over the United States. Families received telegrams saying their sons or husbands had died in crashes, but the causes were classified, so families never learned that faulty engines had killed their loved ones. After Gilbert's modification, the death rate from engine problems dropped to near zero. 97 men had died before the solution was found. How many hundreds more would have died if Gilbert hadn't discovered the crushed baffle fix? The Air Force never calculated this number, but historians estimate at least 400 additional deaths. That means Gilbert's contribution saved roughly 400 American airmen. Each of these men had families, futures, potential contributions to society. Gilbert's work preserved all of that potential by preventing senseless deaths. He never met most of these men, never knew their names or stories, but they lived because he spent a night in a hangar with a hammer and a pyrometer. The strategic impact of Gilbert's fix extended beyond World War II. The B-29 became the basis for America's nuclear deterrent in the early Cold War. Strategic Air Command relied on B-29s to carry atomic bombs and threaten Soviet targets. This deterrent capability required reliable aircraft that could fly long missions without mechanical failure. If B-29 engines were still exploding at the 1944 rate, the deterrent wouldn't have been credible. The Soviet Union would have known that American bombers couldn't reliably reach their targets. Gilbert's modification helped maintain the nuclear balance that prevented World War III. This connection between a crew chief's hammer and global nuclear strategy seems unlikely. But that's how history works. Small technical improvements enable large strategic outcomes. The lesson from Gilbert's story applies broadly beyond aviation. Complex technical problems often have simple solutions if you look in the right place. The right place is usually where the problem actually manifests, not where theory says it should be. Gilbert looked at actual engines under actual operating conditions. He took measurements, noticed patterns, and tried modifications based on evidence. This empirical approach is fundamental to good engineering and science. Theory guides where to look, but evidence determines what's actually true. When theory and evidence conflict, evidence wins every time. The story also illustrates the importance of having diverse perspectives on technical problems. Wright's engineers all had similar training and similar approaches to problem solving. They thought about cooling in terms of calculations, theoretical models, and design optimization. Gilbert thought about cooling in terms of metal temperatures, airflow paths, and what he could feel with his hands. His different perspective let him see solutions the engineers missed. Organizations that encourage diverse viewpoints are more likely to solve difficult problems. This doesn't mean hiring people with diverse backgrounds just for the sake of diversity. It means actively seeking input from people who think differently and have different experiences. The mechanic might see what the engineer misses. The customer might notice what the designer overlooks. Good leaders create environments where these diverse perspectives can be heard and acted upon. As we conclude this story of how Staff Sergeant Jeff Gilbert saved B-29 engines from exploding, several themes emerge clearly. First, practical experience and careful observation can solve problems that theoretical analysis misses. Gilbert succeeded because he took actual measurements on real engines rather than relying on design calculations. Second, simple solutions are often better than complex ones. Crushing baffles with a hammer was crude but effective, solving a problem that stumped engineering teams. Third, organizational hierarchy shouldn't prevent good ideas from being implemented. Gilbert was a sergeant, but his solution was better than what colonels and corporate engineers proposed. Fourth, leadership matters enormously in enabling innovation. Major Ross and General Ent took career risks to implement Gilbert's fix quickly. Their willingness to bypass bureaucracy saved hundreds of lives. Fifth, evidence should trump authority when they conflict. Wright Aeronautical insisted their design was correct, but Gilbert's temperature data proved otherwise. The Air Force correctly chose to trust evidence over the manufacturer's assurances. These principles remain relevant today in any field involving complex technical systems. Whether you're designing software, developing medical devices, or building spacecraft, the lessons apply. Test your assumptions with real data. Listen to people with hands-on experience. implement solutions quickly when evidence supports them. Jeff Gilbert never set out to revolutionize aircraft engine cooling. He just wanted to stop watching good men die in preventable accidents. His solution, crude as it was, enabled the B-29 to become the war-winning weapon it was designed to be. Every B-29 mission over Japan flew on engines modified using Gilbert's technique. The crews who dropped bombs on Tokyo, who mined Japanese harbors, who flew reconnaissance missions all depended on engines that wouldn't explode. They probably never knew that a crew chief with a ball-peen hammer had saved their lives. But Gilbert knew, and that was enough for him. The next time you see a restored B-29 at an air show, remember the cooling baffles inside those massive engines. Remember that they were modified by hand, one by mechanics following Gilbert's technique. Remember that innovation doesn't always come from laboratories or engineering departments. Sometimes it comes from a maintenance hangar at 2 in the morning, from someone who refused to accept that things had to keep failing. Jeff Gilbert's crushed tube fix didn't just save engines, it saved the crews who flew them. It enabled missions that shortened the war and prevented a costly invasion of Japan. And it demonstrated that sometimes the most important innovations are the simplest ones. All it took was a hammer, a temperature gauge, and someone willing to question assumptions. If you found this story as compelling as we did, please take a moment to like this video. It helps us share more forgotten stories of innovation and courage from aviation history. Subscribe to stay connected with these untold histories. Each one matters. Each one deserves recognition. And we'd love to hear from you. Leave a comment below telling us where you're watching from. Thank you for watching, and thank you for keeping these remarkable stories alive.